This week's webinar is a brand new one from us, and it is around RIBA 2030 and some practical case studies. Richard Bowman, who is poised to talk to you about these projects, is going to be up next, and he's going to do the bulk of the talking on the projects. I'm just going to do a quick intro and just remind you guys that try and keep your mics on mute. Do put your videos on. It's always great to see some faces. And if you've got questions, and hopefully there will be a number of questions this time around, feel free to open the chat box and type a question in. We'll get them answered at the end. We've got, just by way of, as I say, a really quick intro, Richard is one of our kind of key consultants in the practice. He specialises in overheating, a long list of various, criteria for judging buildings, and has got his head around RIBA 2030 as well as the rest of the practice in the last 9 months or so. And we've been lucky enough as a practice to very quickly find clients that are willing to have a look at their projects and see how they meet the criteria. And so, as I say, Richard has done the bulk of the analysis on that. He's going to run you through three different projects. So without further ado, I'll hand over to Richard. We'll try and wrap it up by 10:45, and then we'll leave 15 minutes at the end for questions. So Richard, over to you.
Thanks, Doug. Good morning, everybody. So what I'm going to do this morning is talk through 3 projects that I've had the pleasure of working on over the last few months in the context of the RIBA 2030 Climate Challenge. I'm going to focus on the 3 projects. Each one has been chosen for a specific reason. The first one will look at operational energy demand. The second will be looking at embodied carbon, and the third one will be looking at how we can tackle reduction in the use of potable water. The first project is a commercial project. It's the redevelopment of Snug Architects offices by Snug, situated in Southampton. And basically what they're undertaking is a commercial extension of their building. They want to add a second floor. And they're ambitious in that they see the benefits of RIBA 2030. And we've been undergoing a sort of iterative design process where we've taken the original sawtooth design, and as we've worked through the project, it's undergone a few changes. The targets we're looking at for RIBA 2030 is to try and reduce the operational energy as far as we possibly can. And what the RIBA would like is to see buildings over the next 10 years be consuming less than 55 kilowatt hours per metre square per year. What is important to remember is that the operational energy is, if you're familiar with Part L, is concerned with both the regulated and unregulated load. So we're concerned with the mechanical and electrical services, but also the plug loads, whether it be from computers, kitchen appliances, cooking equipment, fans, and so on and so forth. So it's a little bit more ambitious than just achieving compliance at Part L. So the challenge here really was to reconcile building performance with cost, to stay within a budget, and also refurbish the building effectively to support the practice as they grow. And the building at the moment, the design has changed to look what you can see in front of you on the screen now. So it's an overall fabric first efficiency upgrade, which meant that operational energy overall was reduced by 78%. And we were able to achieve passes at CIBSE TM52 for overheating. So we know that natural ventilation will keep the building cool. There's been a number of design tweaks along the way regarding glazing and so on and so forth, but that's sort of part of the design process, really. What that meant was we can actually make the building very low carbon by looking at the fabric and the services. So the graph in front of you was the recording of the Part L compliance for either retaining the existing gas system or replacing it with a more efficient air source heat pump system. So as you can see, by keeping the fabric consistent and changing the array of PV that we're proposing for the roof, we're able to either achieve pretty much carbon neutrality either with an air source heat pump or gas, depending on the amount of panels that are put on the roof. But at the same time, we decided to have a look at if you were building this building from scratch, what you would achieve in comparison with a refurbishment. And as you can see from the graph on the right-hand side, we made a drastic jump in ambition for the fabric of the building to see what the impact of that would be, which meant that with either retaining the existing gas system or introducing air source heat pumps, there would be a significant reduction in carbon, so that we would actually be carbon negative on the building. What we also decided to do was then look at operational energy in detail in the context of the RIBA 2030 targets. So on this graph, you can see the red line representing the current benchmark set by CIBSE, and then the targets RIBA would like buildings to achieve over time. I went through a number of stages. So looking at the graph from the left, we have the as designed solution. Not in the as designed solution, because of various contributing factors, not all the fabric has been improved. And therefore we would achieve, but then by switching out the gas for an air source heat pump and make a significant improvement so that the building would achieve its 2025 targets. And then if we were building this building from scratch, then using the gas or the air source heat pumps, we would get very close to the RIBA 2030 target. In fact, it was a kilowatt hour above the benchmark for RIBA 2030. And then the client wanted to know a bit more about the difference between what that meant if it was just the regulated load. So it's a bit like when we look at Part L, we sort of make the distinction between regulated and unregulated loads, and they wanted to get an understanding of that at the same time. And so by subtracting those unregulated loads from the dynamic thermal model, we were able to look at comparison and how much the building would reduce its energy consumption under those circumstances. What we then decided to do is that I asked for a year of utility bills. So we undertook what was effectively a kind of an energy desktop PO, post-occupancy evaluation, to understand what energy was actually being used for plug-in loads, lighting, and so on and so forth, and for electricity, compared with what is deemed sort of acceptable targets if you're designing a building from scratch and you haven't defined what your plug-in loads are likely to be. And then what we found was that if we applied the actual plug-in loads and applied that to the new floor area, then the gas operational energy was certainly below 2025 targets. And by using a very efficient air source heat pump, we could certainly meet the RIBA 2030 targets with the refurbished building, and then certainly with the building if we were constructing it from new with some very ambitious U values. So what that meant was we were able to basically, in comparison, reduce gas operational energy by half. Same for the air source heat pumps. And then if it was new build operational energy, we'd be getting down to between 34 and 56 kilowatt hours per meter squared for the building. The second case study is a project called Hope Street. Again, this is in Southampton. It's for a charity, very similar to if you've heard of Maggie's. The stakeholders, the client is one small thing, and we're working with Snug Architects. The sustainability ambition is very high. The client from the outset has specified BREEAM outstanding, and it's recently gained planning approval from the Southampton City Council. What we did at a very early stage when we started to consider embodied carbon, and embodied carbon being the carbon of the products and materials that are used to construct a building from extraction through to assembly on site, is that we started looking at the BRE Green Guide to Specification, and in considering the aesthetics that the architect wanted to achieve, such that 2/3 of the products are actually A and A+ rated. Another third roughly are B+ rated. And in fact, the only C rated product or principle of construction in the building is actually the ground floor slab. So in terms of the challenge, currently buildings have embodied carbon targets of about 1,100 kilos of CO2 per metre squared. The ambition is actually to really reduce that by over half over time. And so what we did with the architect is adopt some ambitious U values, because we knew this would have the benefit of reducing heat losses by taking a fabric first approach, which then would have the knock-on effect of reducing the energy demand on the building. And what that meant was, for the building to the hub at the front, we reduced carbon emissions by 60%, and for the building at the rear, we'd have reduced carbon by 92% in terms of Part L. After that, we then exported the IES BIM data to One-Click LCA. One-Click LCA is a carbon calculation platform which interoperates with IES. And what this meant was we could export all the geometry and the volume and areas of materials into this calculator, and very quickly start to play with different types of construction and building services strategy to get a measure of what the embodied carbon was likely to be. And it was very reassuring to find that actually the preferred principles of construction of cross-laminated timber with the renewable energy strategy that we proposed was bringing the embodied carbon down to about 400 kilos of CO2 equivalent per metre squared. So we knew we were at a good starting point. We then looked at this in more detail with the architect, and we refined the principles of construction. So actually at stage 2, the embodied carbon result was just short of just below 200 kilos of CO2 equivalent. Because of the cross-laminated timber, the actual amount of sequestered carbon contained in the timber construction was nearly 600,000 kilos, with a whole life carbon of about 1,000 tonnes over the 60-year life cycle of the building, and with a life cycle cost of 9.7 million. And that life cycle cost captures all the energy costs, maintenance and repair, and so on and so forth. So we've got a good picture of how the building was likely to perform and cost over its lifetime. At the same time, because it's a BREEAM project, we're having to also look at overheating. And we initially looked at overheating from a natural ventilation point of view. So by applying the window opening strategy from the architect's drawings into the IES model, we were able to establish that the commercial aspects of the project at the front of the building would pass TM52, and the residential building at the rear would pass CIBSI TM59. So CIBSI TM52 is used for non-domestic properties to establish overheating, and CIBSE TM59 is the more recent addition to establish overheating in residential buildings. And it was also reassured the client that we would actually, 98% of the time, the operative temperature would meet CIBSE Guide A criteria for both the office and the housing at the rear. It's worth bearing in mind that the overheating is very low, but what is worth also bearing in mind is the facade I'm looking at, pointing to at the moment, is actually the west-facing facade. And because of the constraints of the site, there's very little room to manoeuvre in terms of where we could put glazing, and so there was plenty of overshadowing. So when we were looking at the daylight factor at the same time to balance that with the overheating, we found that actually 72% of the occupied floor area had a daylight factor of 2% and above. 2% really being the point at which you were less likely to use electrical lighting and save energy, so it's a plus point. And the housing to the rear actually had less natural daylight. So because of the orientation of the glazing, we reduced the overheating was reduced, but at the flip side, there's probably less daylight, natural daylight, than we would prefer. The third case study we undertook for Southampton City Council regeneration. And this was done in the context that they would look, Southampton need to build roughly 10,000 homes over the next few years to meet housing demand. But at the same time, they didn't really have a benchmark to work with as to how they would deploy this housing and how it would be designed. And so in the discussions with Snug Architects and Southampton City Council and ACON, we suggested that they look at the RIBA 2030 challenge as a roadmap to sort of improving the performance of the buildings and actually tackling things like fuel poverty, so that we reduce the energy consumption, which costs less, which makes living more affordable and more balanced for a lot of people. So what we did is looked at, took an approach where we'd look at step changes in how the typical house could be altered over time, both bearing in mind new construction products coming onto the market, different construction practices, and actually improving skill sets over the time as to how we actually build buildings. So what we managed to establish was, by working with these targets, is that we could bring embodied carbon down to be better than 2030. With operational energy, we could certainly improve to meet the 2025 target, and potable water we could actually achieve better than 2030 as well. What's worth bearing in mind when you look at this graph, you'll notice that the embodied carbon actually rises, or it dips and then rises between the current design and 2025. And the reason for this is that we took the view that construction practices wouldn't necessarily change rapidly over the next 5 years. And in fact, a lot of the constructions we use today would continue to be used for at least the next 5 years. So what that meant was to reduce the operational energy using traditional practice or acceptable practices, is that insulation would increase in thicknesses. So that would then in turn increase the embodied carbon, although it will bring down the operational energy. So in terms of how we approach this, we set a step change approach to the energy strategy, so that the heating profile was generally intermittent and then became more specific as time went on. So really being mindful of maybe behaviour change and how people use energy as we become more energy aware. The system would migrate from gas to electric, where we'd use either a community-based ground source heat pump with underfloor heating, and probably something like triple fin radiators to the upper floors. The reason for that being was that if you have underfloor heating in a bedroom, then wherever you put the bed, you're going to not reap as much benefit from the heating as you would otherwise. And solar would gradually increase from sort of 2 kilowatt peak to 4 kilowatt peak. 4 kilowatt peak is a typical sort of 10 to 12 panel system. And then ventilation would actually move from being natural and intermittent, so trickle vents, window opening, to mechanical ventilation with heat recovery. The benefit there being that really in the, especially in the winter and the heating season, that you're bringing fresh air into the building and retaining the heat that you're generating. So you end up with a more efficient use of your heat energy. And then there would be a window opening that would occur. This would be by people opening windows. So what we'd do in the model is have a formula which basically allows for windows to be simulated being up to 30% open in the winter, 60% in the spring and autumn, and then 100% open in the summer for purge ventilation. And internal doors would still be open to different degrees for natural cross ventilation during the day, but would be closed for privacy at night. Again, very similar to the Hope Street project, we took a step change approach to the fabric first. So over time, there'll be more recycled materials with a super insulated fabric. So sort of improving U values by a significant amount. I mean, we're talking in the region of 80 to 100%. And that air tightness would gradually improve from sort of the acceptable 5 down to 1 in tandem with the mechanical ventilation and heat recovery being implemented. But the focus of this project, or for this case study that we'll talk about, is really the RIBA 2030 Climate Challenge potable water use targets. So currently it's acceptable for water usage to be about 110, 125 litres per person per day. And what the RIBA have asked people to consider is that we would actually try and reduce that to below 75 litres per person per day. Now, we can actually get below 2025 targets quite easily today, and most of that is through the use of more efficient fixtures and fittings. So having a smaller dual flush WC, changing flow rates on showers and taps, and actually reducing the volume of the bath. But then the real question is, well, how do you get from 2025 to 2030? And this requires sort of more ambitious thinking, I think, but also helps people in the long run. The solution there really was to suggest a transition away from baths as the sort of the large water consumer object of the property. And what that meant was, if we moved to wet rooms instead of bathrooms, then we could get down below the RIBA 2030 target. And what that meant was you end up with a bathroom in a house, or now a shower room in a house, that was more adaptable, so more flexible for in sort of lifetime homes way of thinking, and maybe sort of more limited physical access. Something that did come up in the conversation was, well, should we use rainwater? There's mixed views on that. It does, the reuse of rainwater does allow us, in this case, to reduce water usage below 55 litres per person per day. However, it does bring complications in that you need secondary plumbing to be able to move that water from sort of the rainwater harvesting tank, which would typically be buried in the back garden, back up through the house and reuse it in either the toilets or washing machines, for example. But it is achievable, although it was not pursued in this case. So bringing this all together, what I've been able to do is really start to establish a design process to sort of bring together all these different considerations into sort of a more holistic thinking. I'm sure many of you on the call will be familiar with the RIBA plan of works and the sort of stage 0 to 7 circle. And what we're trying to do is put design concerns about embodied carbon, operational energy and water into the context of the 3 pillars of sustainability, i.e. the social, the economic and the environment. And what we've learned over time is the best way, one of the best ways to approach this is very early on is to, when you're working with clients, is to set the aspirations of the project, which will carry on through. And then as you get into stage 1 and setting out the brief, is to try and define those unregulated loads that are such a challenge when it comes to Part L. And the reason for that is that there are numerous case studies now where buildings have achieved Part L compliance, and then once you reach the aftercare or post-occupancy stage, is that operational energy is proving to be up to 4 times what it was expected to be in the Part L compliance calculation. And so that has significant building life cycle cost implications for the owners of the building and the users. So what we've managed to do is really boil this down to sort of strike a balance between those 3 pillars of sustainability. The benefit here is sort of reducing design risk. And this sort of design process really works in pretty much any direction. And it sort of really highlights the interrelatedness of different aspects of the design process. So, for example, we've got the social considerations surrounding the form of the building and whether it overheats, whether there's sufficient natural daylight, whether the indoor air quality is sufficient for the occupants to use the building comfortably. And then there's the interaction between the form of the building and its use and the appropriate energy strategy. What is the most appropriate principle of construction to bring down the embodied carbon? And then how we relate that sort of more tangible elements of the project in terms of the materials it's made from with overheating and daylight. And really the outcome from that is to establish leadership in sustainable building design and performance. It's sort of balancing those 3 pivotal points and sort of achieving that optimized design for the future.
Great. Cheers, Richard. That was a kind of a whistle-stop tour through some of the case studies that we've done. Hopefully, you can appreciate from that, from those projects, this is not an easy problem to solve. There's a lot of different things going on, and the only way that we can really make headway in this is by changing process and better utilising analysis and sharing of information. I've got a couple of questions. Feel free to put your questions in the chat box, guys. I know Patrick and Angus have been talking about water. I think the big question that the guys have got at the moment, Richard, is there's concern that certainly trying to meet the RIBA 2030 standard, you know, getting rid of baths out of houses may not be practical for, you know, families with young kids and stuff like that. So, you know, what's your, well, I guess it's a two-part question. One is, how is water usage actually calculated by Part G? Again, for those who aren't familiar with how water usage is calculated. But to meet those really rigorous targets at the end of the decade, are we honestly imagining that every house has to be designed without a bath, or do we think there are other ways of achieving those targets? So thoughts on that?
I think in terms of the baths, it's a tricky one. It's a deeply embedded cultural element to sort of our lives, and that doesn't matter where you go in the world. You know, you've got bathing has been around since sort of Romans. You know, you still get communal baths in places like Japan and Turkey, and you know, it's very much part of our culture. I think it requires a step change in how we deal with water stress, and that's the real driver behind the RIBA target. Is that, especially in the UK, you know, more and more of the UK is under water stress these days, especially in the summer, and so we have to make better use of our water. So it's a case of balancing the need to change how we use water with how we design our buildings to balance that out, really. Okay, cool. Just looking at a question here from Charles. He's talking about, he's saying, I'm interested in the move away. So this is on the Snug project where we did the office extension to the top. You showed one there with the kind of sawtooth roof there, which I think was design number 1 out of 3. And he's saying, I'm interested in the move away from a north-facing artist's light sawtooth to the preferred design. What was the effect on light levels? And I presume this provided an acceptable level of operational light. So he's picked up on the fact there that the design's radically changed. What was the effect on kind of light levels as an effect of that? So was that detrimental, or did, you know, was it okay, you know, given the real change of design? So obviously, windows in that one. Yeah. The initial design, the proposal for the new first floor studio had fantastic daylight. I can't deny that. It's all north light. The sawtooth roof provided a fantastic opportunity for south-facing solar PV, and so it was a great, it was a good sort of airy loft-like space. But there was also a desire not to make it too industrial from the architect's point of view, and so by the time we got to this space, I mean, this is actually quite interesting, because what you can't see from the model is that there is actually a mezzanine floor within the vaulted roof space, with actually sort of an opening sort of around the edges. So, and then to the north, there was still half the gable end is still open glazing. So there's quite a lot of daylight from there, and also from the roof lines. But what was interesting is that the room layout was designed specifically to make the most of the daylight on the ground floor level. So the area of interest where the desks are is actually predominantly where the glazing is. With more sort of circulatory area in sort of below the mezzanine floor, and then the roof lights providing more than ample daylight into the mezzanine floor itself. There were design tweaks to the dormer element, so that, you know, originally it was to be a polycarbonate sort of facade that would effectively glow. But we sort of, over time, to meet the TM52 requirement, had to reduce the amount of, well, we changed the south facade, so that's actually a solid facade with rain screen cladding, and then reduced the north side glazing, but also made more open area in the north and west facade on that dormer. But there were limitations there, because the west facade actually faces quite a busy road that leaves Southampton via Tottenham, so that we're conscious of keeping external noise out of the building as well.
And just to, if you're at all unsure, I mean, there were quite some big design changes on this project. This was solely primarily down to cost. It was nothing to do with trying to meet the RIBA framework. We started out in one place, and it became clear that there wasn't as enough money in the pot as had initially been hoped. So that's why the design was changing. That wasn't us saying, oh no, to meet RIBA targets, you've got to completely redesign the building. So if you were unsure about that, hopefully that's clarified that up. Sophia was asking, just sticking with daylight, Richard, interested in that play in Hope Street between daylighting and overheating. So, the more daylight you let in, the greater the chances of overheating. And she actually, I don't know what your familiarity is with the LETI guidelines, but she's saying, I mean, obviously those are guidelines, but as far as glazing is concerned, the glazing to solid ratio or solid wall ratio is quite dire. So I'm guessing pretty poor as far as daylight is concerned. Are you familiar with the LETI guidelines and have you got a...
No, I've tend to work with the BREEAM guidelines and the CIBSE lighting guides.
Yeah, I mean, it does, again, it picks up on this subtlety between design and performance, and it is becoming far less obvious about what is the right design solution, what is the right design tweak to meet increasing compliance. And one of the things, I was just going to take a step back from the questions that were being asked to ask a more wider question, Richard, here, which was, we've covered 3 fairly different projects here, but just to give the audience an idea, at what stage were the projects at when we got approached? So the clients had a goal, they had RIBA 2030 in their mind, some of them did, certainly Southampton County Council didn't, they were looking for a framework. But generally speaking, what stage were practices at when they came to us for help? How far advanced were they with the design?
The Southampton one, for Southampton City Council, was effectively writing, as a team, we were writing the brief, because we were trying to demonstrate how so volume housing could be built for social reasons by a local government, and it had to be demonstrated to the policymakers, or sort of that would be sort of voting to put these policies in place. So that was very early on. The Hope Street project, we joined that pre-planning. So just the beginning of RIBA stage 2. And the Snug office, that was at the beginning of RIBA stage 2. It's still pre-planning at the moment.
Yeah, okay. And I know certainly with the Hope Street project, and again, this is worth explaining here, as Richard talked about it, with the kind of the Venn diagram he showed in one of his final slides there. Certainly the Hope Street project was keen to push on and move out of that initial design phase and kind of get planning. And that caused some real practical issues with iterating the design, because timescales and construction program were forcing the hand detrimentally of properly thrashing out the design for the benefit of the project. And I would say, one of the lasting comments here, and we see this over and again, and this is the way that in my mind process is having to change, is there has to be more time and more consideration in stages 1, 2, and 3, particularly 2 and 3, to thrash this analysis out, to really get goals down, to really get the important things which affect design and design affect the results and cost. All of these are bundled in before moving into stage 4. And this is going to be difficult for some practices at the moment because of the way that they work. But to really get the very best out of the project, you've got to add some more time at these stages. And one other question I had, Richard, again, for the wider benefit of the group here, is once we were involved in the project, just discuss in kind of practical terms how we did this analysis. What meetings did we have? How did we iterate the design? What information did we get from the architects or the design team? And then how did we give that feedback? it wasn't just a one-way transaction. We told them what to do. It was very iterative. So just describe how that would work for, say, somebody who came to us with another project.
Yeah, I mean, it's very much for me, a close working relationship in designing buildings. For example, when we were looking at Hope Street, the striking a balance between the overheating and the natural daylight required, I think, before planning, we actually went through 5 different iterations of the model. So although the actual form itself was fairly fixed, we did a lot of work with the architect in looking at borrowed daylight, for example, how we would change the fenestration design for window opening, for natural ventilation, and as you're exploring one, you then have to go back and explore the other as well. You can't say, well, for example, I want to have a nice glazed wall because we're going to have a fantastic view, and that's fine. We're going to hit our daylight requirements, and then find that actually between sort of 9 and 11 a.m. in the morning, that room is going to be overheating, and there will be no amount of effort that can be made to increase the opening in the glazing that will actually help keep that room cool. So it's a very much a balancing act for those two. The same goes for the principles of construction and embodied carbon. I'm working on a project at the moment where we've already tested the overheating and the daylight, and that's satisfactory. And it will the indoor air quality will be fantastic. But what we've moved on to now is actually looking at the embodied carbon and the principles of construction. What I did for that, because we're at very early stages at the moment, we're sort of really on the cusp, the tail end of stage 1 going into stage 2. Is the mesh embodied carbon calculator as a nice, simple, quick tool. And by using that, we're able to very quickly explore different principles of construction while calculating the embodied carbon, and then explore different iterations of that design of that construction in meeting the 2030 targets. Could we actually achieve RIBA 2030? So yeah, I mean, that's another good example of it. The form and orientation, I think the Snug office was a good, interesting exercise, because we were able to constantly explore different principles of construction. So that was set quite early on. We carried, once we knew we would achieve a certain embodied carbon for certain principles of construction, that then carried through the different design iterations against the value engineering exercises that were going on. And so while the value engineering exercise was going on, we were then constantly looking at overheating and daylight and working with the architect to tweak the design and to make that improve. So to get satisfactory daylight, for example, and also in achieving that daylight, look at how much of those glazed areas would need to be open to meet the TM52 overheating criteria.
Yeah, I mean, the analogy that you were talking about there about kind of plate spinning or juggling, I can't remember exactly what one was, it is a really good one. I mean, it's every project will have its different priorities. Just because you're aiming to meet RIBA 2030 criteria, there will be some aspects of the project which you feel more strongly about that need to be concentrated on, or the client does, or somebody else does, one of the other stakeholders. And it's important to understand that, by single-mindedly chasing embodied carbon, you can start really losing track of operational energy and cost and other things. And you've got to constantly, as you're iterating the design, keep these other plates spinning and just make sure one of them isn't just about to wobble and crash to the floor. So you've got to juggle all of those things at the same time. And this is why it takes more time to understand where those sweet spots are, where you can make advancements for an allowable cost and allowable change in dimension or an allowable area of something, to make sure that you end up with win-win-win-win-win across the board, rather than a big win and lots of losses. You know, essentially what we're talking about here is, if you go down this route, whilst it requires a change in process, you can rapidly increase project risk, unknowingly design risk, by trying to do the right thing. So by trying to do the right thing, you actually put the project more at risk of not meeting these kind of criteria that you want to hang you know, the project's hat on and make a big marketing shout about. There's a couple of other questions in the comments section, but again, what's really helpful here, we try and be as transparent as possible. So I want to talk to you guys about cost. So one of the other projects that we haven't featured here, which is actually a new build house that we're doing for somebody, and the work that we did for Snug Projects on their office extension, they were actually very, very similar in pricing. And those came out, so to do the analysis that you've seen here, to find out where they are, to optimize it, is around the kind of the £3,000 mark to get that done. On bigger commercial projects, it's more money, but the thinking is very similar. There might be a bit more money on the modeling, you know, the size and complexity of the building. So, you know, whilst you can get indicative ideas for hundreds of pounds, really you've got to be putting a few £1,000s towards it. But the aim of the game here is, if you spend that money at the very early stages, you save a considerable amount of time and effort and money further on down the line. So as I say, I want to be as transparent as I can do with you guys about cost on that. One other question that we've got from Jamie. Jamie was asking, on the Hope Street project, Richard, you were talking about U values of 0.1 there. So these very tight U values that you get to for RIBA 2030. In Hope Street's case, was that just a case of putting on thicker insulation, or was that choosing better products? And were those based on products of today, or products that may be in the future?
That is based on products today. So what happened at stage 2 is, very early on, the architect issued drawings for their preferred principles of construction, and those principles of construction were really geared up to meet an aesthetic desire on the inside of the building. So you're going to get a lot of exposed cross-laminated timber, but also the outer skin is actually brick for resilience, and so they were trying to balance it up. And then with actually, it's effectively a super insulated cavity, and that carries up through the roof as well.
And we've got the questions seem to have slowed. Just got a final one from Charles, actually, just going back to this rainwater, potable water efficiency in buildings. He's saying it appears that, or is it fair to say that potable water is the kind of the poor forgotten cousin of embodied carbon and operational energy, and kind of gets thought about as an afterthought? So that's one question. But also, you know, he's saying, you know, again, is it one of these things that should be thought about early to really make sure that you can end up with the most elegant solution without trying, you know, compromising at the last minute the design, and try and bolt on things that will save you potable water? So just your thoughts on that, Richard.
Yeah, that's a good point. I mean, it is almost a poor cousin, but in terms of looking at building performance, it's one of the easier challenges to rise to, because the fixtures and fittings are available today. The technology is there, and yeah, pretty much the same way as the energy strategies that we try to employ these days, and making better use of our electricity in heating and hot water. So yeah, I mean, it certainly should not be forgotten, as it's an easy challenge to meet, but it does require looking very closely at the fixtures and fittings and the specification, and thinking about, it's certainly the one that requires a look at behavior change, or what you call choice editing, so that, you know, you sort of, we're trying to sort of influence people and how we approach the use of water.
Mm. Yeah, I mean, there's a lot to learn, and we will find better ways of doing these things and better solutions. But the first thing, as I say, is to realise that it's not easy. It requires some more analysis, and you've got to take stock and think about the design at an early stage to really get the best out of it. You can't do this in stage 4 or stage 5 and kind of making it up as you go along. It needs to be done way before then. Okay.
Actually, sorry, Doug.
Yeah, go on.
What you'll notice when you read the RIBA 2030 Sustainability Challenge documents is that they do make a strong reference to BREEAM as a sort of sustainability marker. And I think the reason for that is that, like you're saying, it does, when you're working on a BREEAM project, whether it's non-domestic or home quality mark, it puts more emphasis on understanding the challenges and defining the project at a much earlier stage. Certainly at stage 2, and certainly setting the aspirations with the client at stage 1. Great.
Thanks, Richard. We'll just spend a bit of time talking about next week's webinar. It goes without saying, folks, hopefully you found that insightful. Again, we're more than happy to talk to you about these projects if they resonate with something you're intending to do. And of course, we're always here to chat about, to see how we can help out. Next week's webinar is, again, a new one for us, really, really special. If any of you are familiar with a little program called Grand Designs, and the paragraph 79 part of the National Planning Policy Framework. Paragraph 79 homes are a tricky fish. And we've got Richard Hawkes, from Hawkes Architecture, that specialises in Para 79 buildings. He's going to be a guest architect. He's the first of a monthly series that we're going to be doing with architects who take a particularly unique angle on sustainability. So the sustainable angle for paragraph 79 homes is quite a high bar, and he's going to be talking through his last kind of 10, 12 years worth of experience, sharing some tricks and tips with you, and talking to you about the tests for Para 79 homes. So if that's something your practice has done, struggled with, you're looking to do, you're excited by, Richard's a kind of a fountain of knowledge. So do tune in for that one. There's already a lot of people booking onto that, so it will be first come, first served. We'll send you out a link later on today with today's presentation, and the details can be found on the website and also on the email that we'll send you out for next week's. So once again, a massive thank you to you guys. Really good turnout today. Hope you found that insightful, and we look forward to seeing you next week. Take care. Thanks very much. Bye.